This section we'll see how to approximate a hypergeometric or binomial distribution of proportions with a normal distribution. This will lead to what's called a one proportion z-test on your calculator. Now remember, if the sample size is large, a hypergeometric and binomial distribution are very close. If the sample size is large, if the population size is large, the hypergeometric and binomial are very close. If the sample size is large, both the hypergeometric and binomial can be approximated well with the normal distribution with the same mean and standard deviation. The larger the values are for n, np, and nq, the better the approximation is. Some people use one of the following rules to see if the sample size is large enough. N is greater than 20, np is greater than 5, and nq is greater than 5, or np greater than 15 and nq is greater than 15. My experience is that you really need np and nq to be even larger for this to really work well. Here are the formulas for a hypergeometric and binomial distribution for the PDF. Sometimes when we use a normal distribution to approximate a hypergeometric or binomial distribution, we use a finite distribution correction. We include all numbers that would round to the correct number of successes when rounding off. For example, if we use a normal distribution to approximate the probability that x is less than or equal to 5 from a binomial distribution with n equals 25 and p equals 0.4, we can approximate the probability that x is less than 5.5 from a normal distribution with the same mean and standard deviation. Notice in this case the approximation is good to the hundredths place since they both round to 0.03 for the probability. So remember, from a binomial, mu is n times p, so in this case that would be 25 times 0.4, which is 10. The standard deviation, sigma, is the square root of n times p times q, so that's the square root of 25 times 0.4 times 0.6, which is about 2.449. And if we want to do the probability that x is less than or equal to 5, that's a normal CDF, or if we use a normal CDF, we go up to 5.5 from essentially negative infinity with a mean of 10 and standard deviation of that amount. And that gives us an approximate value of 0.03309. If we do a binomial CDF for the true probability that x is less than or equal to 5, that would be 0.029. Of course, the binomial is the actual value if it is a binomial distribution, and the normal is approximation from that. And you see that they're kind of close. They're off a little bit, but there is a somewhat good approximation. So let's look at a few examples where we're comparing. Now, as we know, when we're doing distributions of proportions, it's really hypergeometric, because the hypergeometric is when we do sampling from a finite population without replacement, and of course that's really what we're doing most of the time. We very rarely have a situation where we're actually allow the same subject to be answered twice in a survey or be counted twice in a sample. So a sample size n equals 10 usually means 10 distinct items. So that's done without replacement. That's hypergeometric. So let's suppose we're taking a sample size 10 from a population of 40, where there are 15 successes in the population, and we want to say the left-tailed p-value for getting one, if we got one success in our sample of size 10, and that's 0.04 here. If we approximate that with the binomial, when we would get the same probability of success, 15/40, which is 0.0375, we use that as our p probability of success each time on the binomial, and do a left-tailed p-value, we get 0.06. So notice if your decision criteria is alpha is 0.05, we get different conclusions there. If we did a normal without the discrete correction, that is, we only did the probability that x is less than or equal to 1, we would only get a p-value of 0.02. Whereas if we do the finite correction factor, use a normal with this same mean and the standard deviation of let's see, I used the standard deviation from the hypergeometric version. So if we use the standard deviation from the hypergeometric version, and then the the mean from is the same in all three, and then did the probability up to 1.5, then we get 0.046, which is a lot closer to the actual hypergeometric probability. So in this case, here's the actual hypergeometric distribution, which is not perfectly symmetric. Okay, and of course there are actually 10 bars here. The 9th and 10th bar we can't see too well. And then there's to superimpose the normal distribution with the same mean and standard deviation. It's not too good a fit, but it's not that bad either. Now, if the population size gets a lot bigger, like say 160, and here we have the hypergeometric and the binomial compared, and say we get 3 successes at a sample of size 10, and we compare those, say for a right-tailed test, compare these two red numbers here, 0.064, 0.070, we see they're not too far off, but if we do the normal here, or the normal with the discrete correction, the discrete correction, of course, gets it much closer. Without the discrete correction, it's only 0.01, much smaller than the actual p-value of 0.064. With the discrete correction, we get a lot closer, but it's still short by a bit. There's the two distributions there, the hypergeometric and the normal. Now let's get a lot bigger population size, 1,200 for the population size, and this day we get a sample size of 50. Okay, and now we have 35 successes in the sample, and we'll see what we would get for different two-tailed p-values down here to compare some. 0.18 would be the actual value. 0.19 is what we would get if we use the binomial instead of a hypergeometric. 0.14 is we use a normal and we do the probability up to 35, but if we go up to 35.5, we would get 0.18, and it's actually that one's actually pretty decent. And of course now the two graphs are starting to look pretty close. There's the hypergeometric graph and the normal approximation. If we're just comparing a binomial and a normal, then here's an example with a sample size of 90, and we get 62 successes. We do a left-tailed p-value there, 0.004, and the normal, if you go right up to it, up to less than or equal to the 62 there, we get a 0.004, but the discrete correction throws it off a bit. That's comparing the normal and the hypergeometric and the binomial. Here's another comparison. So if you'll notice, when we get bigger, the bigger sample size, these start to line up a lot better. There's another one to look at. There's another example. So most textbooks exclusively use a normal distribution approximation of a binomial or a hypergeometric distribution when performing inferences about proportions. Unless a homework problem that we should actually use a hypergeometric or binomial when we should use it, and we will allow a normal approximation in some cases. So in this class, we will compute p-values for hypothesis tested proportions by the correct hypergeometric distribution when the population size is known, and by the binomial distribution when the population size is unknown but large. In a subsequent video, we will continue to talk about using a normal approximation of a binomial or hypergeometric distribution when performing inferences about proportions, including confidence intervals as well as hypothesis tests. We will use these approximations when specifically directed to do so in the problem. Techniques using binomial distributions really should always be used and are critical when the sample size is small. Furthermore, the hypergeometric distribution should be used to compute values when the population size is given. This is critical when the population size is small.